Okay, so again, I forgot to hit the record button on the class session yesterday. We wrapped up in the first half of class talking about dot products of vectors. So the first definition, if you're given two non-zero vectors u and v, their dot product is going to be, okay, first of all, the dot product over here on the left. The symbol that you use for that operation is just a dot, like a multiplication, although this isn't really a multiplication because vectors aren't really numbers, so that's why we call it, instead of multiplication, a dot product. And on the right-hand side, the dot product is the product of the magnitude, so you take the length of the vector u times the length of the vector v times cosine of theta, where theta is the angle between u and v, and it's the angle that's between 0 and 180 degrees. So, what this means, right, you might be given a couple vectors. You can put their tails together. Right, there's two angles here. There's this smaller angle right here. That one I would call the theta because that's going to be between 0 and 180. There's also this larger angle right here, except for in this case that angle would be greater than 180 degrees. So we would take the angle theta between the vectors to be the one labeled in red. If u is 0 or v is 0, then the dot product equals 0, and the angle between those vectors is undefined in that case. It doesn't make sense to talk about an angle between vectors if one of the vectors is the 0 vector. Okay, so with that definition in mind, we can talk about how to determine if two vectors are orthogonal to each other. We say that u and v are orthogonal if and only if their dot product is 0. The 0 vector is automatically then orthogonal to all vectors. And what we mean by orthogonal is just that two non-zero orthogonal vectors are just vectors that are perpendicular to each other. So if you join them at the tail, the angle between them would be 90 degrees. So knowing that the angle between the vectors is 90 degrees if they're orthogonal, if you go back up to the formula for dot product, okay, if two vectors are orthogonal or perpendicular, the angle between them would be 90 degrees. But cosine of 90 degrees, cosine theta in that case, would end up being 0, and that's why you would get a 0 dot product. So let's do an example. So now we're going to find a dot product if u is equal to a vector with components 3, 0, and then we're going to dot that with a vector v that has length 10 and points 45 degrees above the positive x-axis. So pictorially, what we have in this setup, here's the xy plane. Maybe here is 3 on the positive x-axis. Okay, so the first vector u starts at the origin and points 3 units to the right. The y component is 0, so you wouldn't be going up or down. This vector would be on the positive x-axis. And the vector v has length 10. Oops. So this is the vector v. This is the vector u. And we're told that while the angle v is pointing 45 degrees above the positive x-axis. So this is a 45 degree angle, and that also consequently ends up being the angle between the vectors. So now when I do the dot product u dot v, that's magnitude of u, magnitude of v, cosine of the angle between those vectors. Now since u has no y component, it's just going 3 units to the right. We already know that the length of u is 3. You could also do the square root of 3 squared plus 0 squared. That would also give you 3. Vector v is given, the length of v was given to us as 10, and then we're going to multiply that by cosine of the 45 degree angle. 3 times 10, that's going to give me 30. And then cosine 45 degrees we know is 1 over root 2. So in this case the dot product is this 30 over root 2. Okay, now I should say this, the dot product doesn't really have necessarily a geometric interpretation. The main uses of a dot product are to, one, determine if the angle between vectors is 90 degrees or if two vectors are orthogonal. The other benefit to the formula for the dot product is there's going to be an alternate formula for the dot product, and that's going to allow us to use this formula and find the angle theta between the two vectors. Okay, so ultimately the dot product is useful for finding angles between vectors or determining if two vectors meet at a 90-degree angle. Okay, so the other formula for a dot product, if you look in the box at the top on the next page, given two vectors u with components u sub 1, u sub 2, and the vector v with components v sub 1, v sub 2, the dot product is just the product of the x components plus the product of the y components. And then I'm not going to go through the proof of this. There is most likely an explanation in the textbook. Now, we're going to use the second definition on the previous page, that two vectors are orthogonal or meet at a 90-degree angle if and only if the dot product is 0. So what we're going to do is we're going to determine if the following triangle, in example 9, is a right triangle. So what we're going to do is, at each of these points, we're going to form vectors that have that point as the tails of those vectors. We'll take the dot product. If it's not equal to 0, the angle between those vectors is not a 90-degree angle. Okay, so first of all, there's a little angle right here. I'm going to call that beta. Now we're not actually going to find beta. We could use triangle trig if we wanted to. We'd have to maybe find the lengths of all the sides, which might be more cumbersome than we would like. But we are able to determine if beta is 90 degrees or not. Now what we'll do is, with r being the tail, we're going to look at two vectors. So for the angle beta, we're going to, sorry, I'm having some issues with my stylus. So for beta, okay, we're going to consider the vectors RQ and the vector RP. Okay. So I'll write them on top of each other. Now, remember, if you have a vector going from one point to another, the x component would be the, in this case, the x coordinate of q minus the x coordinate of r, and the y component would be the y coordinate of q minus the y coordinate of r, and the vector rq then would be the vector 3 comma minus 4, and then the vector rp, the x component is going to be the x coordinate of p minus the x coordinate of r, and then we're going to take the y coordinate of p minus the y coordinate of r, and this vector would have components -3, -9. And now, when you do the dot product, RQ dotted with okay, unfortunately my link to the computers had gone awry there, so we were in the middle of looking at this angle beta, and we wanted to determine if it was 90 degrees. So we looked at the vector RQ, and that had components 3 minus 4, and we looked at RP, which had components -3, -9. And if you take the dot product, RQ dotted with RP, that's That's the vector positive 3, negative 4, dotted with negative 3, negative 9. This equals 3 times minus 3 plus negative 4 times negative 9. That's the formula of the dot product. And this will give us negative 9 plus 36, certainly not equal to 0. Okay, so what this implies is beta is not equal to 90 degrees. Okay, so that angle is not going to be a right angle. Now, this little angle in the bottom left, if I call that alpha, okay, that's certainly, you can do the same procedure, just take my word for it. It's not going to be a 90-degree angle. The dot product of PR and PQ will not be 0. So what I'm going to do is I'm just going to call this angle here theta, and we're going to see if that's the only angle that possibly looks like a right angle. So we're going to see if that is 90 degrees. Okay, so for theta, we're going to look at the vectors QR, find its components, and then we're going to look at the vector QP, find its components. Now QR is just the vector in the negative direction of RQ, or you can think of it this way: take the x-coordinate of R minus the x-coordinate of Q, you'll get minus 3, and the y-coordinate of R minus the y-coordinate of Q is going to give you 4. And then the vector from Q to P is going to have an x-component of negative 2 minus 4. So the x-coordinate of P minus the x-coordinate of Q. And then we'll take the y-coordinate of P minus the y-coordinate of Q. And this vector has components minus 4, minus 5. And then we'll do the dot product. And what we get is, so I'm just going to look at the components up here. These red. So if I take the x-component of QR and the x-component of QP, you're going to get negative 3 times negative 6 plus, we'll take the y-coordinate of QR times the y-coordinate of QP, so that's going to be 4 times minus 5. That ends up giving you 18 minus 20, which is negative 2, which is not equal to 0. So theta does not equal 90 degrees either. So this is not a right triangle. Okay. And again, I only did this for beta and theta. The angle in the bottom left corner, I could use the same approach, but you're going to find that that is also not a 90-degree angle, so this is not a right triangle. None of the angles are 90 degrees. Okay, and then lastly, now I said that the dot product formulas weren't necessarily that helpful, geometrically speaking anyways. They don't really give us any quantity like area, or it doesn't help us find lengths of sides, but it does help us find angles between vectors. So if you look at the formula, remember the formula for the dot product is originally u dot v equals magnitude u, magnitude v, cosine theta. You can solve for cosine theta. That's going to be u dot v over magnitude u, magnitude v, and then you take cosine inverse on both sides, you get this formula. Okay, so we're going to go through this example now at the bottom. We're going to find the dot product of u and v using the theorem. We're not going to use the one involving the angle. We'll find the magnitude of u, and we might as well find the magnitude of v as well, and then we'll use those quantities to find the angle between u and v. So for part A, u dotted with v is going to equal just the product of the x components, so 2 times minus root 3, so I took 2 times 1 minus root 3, plus, and then I'll take 2 root 3 times 1 plus root 3. Okay. This will equal, if you distribute the 2 on the left, you'll get 2 minus 2 root 3 plus, and then if you distribute the 2 root 3 on the right, you'll pick up another 2 root 3, and then plus 2 root 3 times root 3. The middle terms will cancel, so you get 2 plus, and then the root 3 times root 3 gives us 3, and then 3 times 2 will give us 6, so the dot product of u and v will be 8. Okay, so that's part A. And then I'll come up here for part B. Now we'll find the magnitude of u and v. So the magnitude of u, this is going to be the square root of 2 squared plus 2 root 3 squared. This will equal the square root of 4 plus, excuse me, and then 2 root 3 squared is 4 times 3, you get 12. That's the square root of 16, so the length of u is 4. The magnitude of v is the square root of 1 minus root 3 squared plus 1 plus root 3 squared. And if you simplify, this will equal the square root of 1 minus 2 root 3 plus 3. And then if you square the 1 plus root 3, you'll get plus 1 plus 2 root 3 plus 3 again. And this will equal, well, the minus 2 root 3 and the 2 root 3 cancels. So you're going to end up getting 1 plus 1 plus 3, which is the square root of 5. Okay. And then part C will come up here. The angle theta now is going to be cosine inverse of u dot v, which is 8, over the product of the magnitudes, which is going to be 4 square root of 5. And you put this in the calculator. Make sure you're in degree mode. And I get that theta is approximately 26.57 degrees. Okay, so that would be the angle between those two vectors. Okay, so I think this is all we made it through, and then I had the video recording at this moment. We went through a bearings question. We started doing a review. So remember, today is going to also be a review. I will record the class session. Anybody has questions, let me know. Office hours 1:30 to 2:30 in the TLC, or make an appointment with me anytime. Thanks for watching, and good luck studying for the exam. Goodbye.